The second phase of matter we will go through is liquids, which retain their volume but not their shape when placed in a container. A solid can become a liquid at a given temperature or pressure, where pressure is going to be defined in this lecture. And the interesting thing about phase transitions is that you either are one thing or another. You have a period where something is melting, but instead of being a material that's somewhere in between a solid and a liquid. It is a solid mixed with a liquid, where each section of the material is either solid or liquid, depending on whether or not it has undergone a phase transition. One of the useful quantities when talking about liquids and large bodies of water or other liquids is pressure. Pressure is defined as the force divided by the area over which it acts, and the pressure exerted on an object in a liquid is given by the weight density, which is the density times g times the depth. The force on the floor of a body of water will be given by how much water is pressing down from above, but the pressure is only given by the density of the water, the gravitational pull on it, and the depth at which the object is at. In this diagram, we have a large but shallow lake and a small but deep pond. The large but shallow lake probably has more force acting on the entire floor because it probably has a lot more water pressing down on it. But the small but deep pond will have more pressure at the bottom than this large but shallow lake because pressure is only dependent on the depth to which you fall. A prominent feature of liquids is Archimedes' principle, which states that an immersed object is buoyed up by a force equal to the weight of the fluid it displaces. This means that if an object is completely immersed in water and displaces an amount of water equal to its total volume, then the force that's going to be pushing back up and pushing it towards the surface is going to be equal to the weight of the water that was displaced. So it's going to be equal to the weight density of the water times the volume of the object that's immersed in the water. This is true of any fluid, whether it's mercury or methanol or water or any other fluid that you can think of. The amount of buoyant force, which is pushing up, is going to be equal to the weight of the fluid that is displaced. So an object placed in mercury, which has a higher weight density than water, is going to experience more buoyant force than an object that was placed in water. Three consequences of this are that an object more dense than the fluid in which it is immersed will sink, an object less dense than the fluid in which it is immersed will float, and an object that has a density equal to the density of the fluid in which it is immersed will neither sink nor float. This is because an object that is more dense than the fluid in which it is immersed will have more weight than the weight of the fluid it displaces, and it will therefore have more force pulling down due to gravity than it will have buoyant force pushing up. An object less dense than the fluid in which it is immersed would be pushed up by buoyant force should it be completely submerged, which means that it would be pressed up until the point where the buoyant force is equal to the weight. If the weight was greater than the buoyant force, then it would sink down. If the buoyant force was greater than the weight, it would push back up. Therefore, it reaches equilibrium and floats when part of the object is submerged, but not all of the object. And then an object that has a density equal to the density of the fluid in which it is submerged will neither sink nor float because the buoyant force is going to exactly equal out the weight of the fluid it displaces. A demonstration of this is that as an object falls down into a liquid, the pressure pushing on both its top and bottom sides is going to increase because liquid pressure increases with depth. But the total force pushing up minus the total force pushing down is going to be your buoyant force, which is going to remain constant. This state of being makes it so that Archimedes' principle is true because the immersed object is always equal to the weight of the fluid it displaces. It's just that as you go down, the pressure increases on both the top and the bottom side, but the net force pushing back up is always going to be constant. A demonstration of the second case, where density is less than the density of the fluid in which it is placed, is a canoe in water. Now, since the volume of a canoe is mostly comprised of air, if you place it in water, it will have less density than the water and will float. However, if a hippopotamus jumps into the canoe, then the density is going to increase quite a bit because density is the total mass divided by the total volume. It will go down lower because the buoyant force needed to press up against the weight is going to be greater. Therefore, the volume of fluid that needs to be displaced to create this buoyant force is going to be greater. And therefore, the canoe will sit lower in the water than it would beforehand. Another property of fluids or liquids is that a change in pressure at any point in an enclosed fluid at rest is transmitted undiminished to all points in the fluid. For example, we have this area A with a 10 kilogram weight placed on it, which is going to cause an increase in pressure directly under it because you're applying a force over an area. This pressure is going to transmit itself throughout the entire fluid and onto the much larger area, which has area of 50 A. Because the pressure is increased, the net force over the much larger area is going to be much greater than the net force that you applied with your 10 kilogram weight, and is going to be able to lift up a 500 kilogram weight on the other side. This is the same principle that is used for hydraulic lifts, which use a small amount of force on one side and lift up a large amount of weight on the other side, such as a car. Surface tension is a property of fluids caused by molecular attractions. Beneath the surface, each molecule is attracted in every direction by neighboring molecules, resulting in no tendency to be pulled in any specific direction. However, a molecule on the surface of a liquid is pulled only by neighboring molecules on each side and downward. There is no pull upward. This means that these molecular attractions thus tend to pull the molecule from the surface into the liquid, and this tendency minimizes surface area. The surface behaves as if it were tied in on an elastic film. Finally, we are going to talk about capillarity, which is the tendency of water molecules to stick to glass or other unlike substances more than each other. This attraction between unlike substances such as water and glass is called adhesion. The attraction between like substances is called cohesion. If you look on the right-hand side, you'll see a series of tubes connected to a bowl of water. You'll notice that the tubes with small diameters or small widths are going to pull the water up much higher because those with small diameters are going to have a greater connection of the glass with the water is going to be attracted to the glass and is going to be able to pull itself up. Whereas those with large diameters are going to have a little bit of adhesion and a little bit of attraction between the water and the sides, but most of the volume of the water is going to be very close to other parts of the water and not very close to the glass. Therefore, it is going to be cohesive rather than adhesive. This capillary action is how trees are able to get water from their base up into their branches through their trunks. They are able to water themselves and get nutrients without having a mechanical pump such as a heart, which we use in order to distribute fluids in our body, but which is unnecessary for a tree.